I will present to you today my work on human-robot interaction and the question of whether and under what circumstances people attribute intentional agency to humanoid robots. So my background is cognitive neuroscience, and I'm interested in human-robot interaction on the human side of human-robot interaction. So we are interested in how does the human brain process signals that are delivered by the robot in a social interaction. And what we typically do is we implement or adapt kind of classical experiments from cognitive neuroscience, experimental psychology, into this kind of interactive scenario that you see. So this is an illustration of a typical let's say methodology that we use in our lab. As our participants are interacting with the robot, we also give them a task. So you see that she has a keyboard through which we can measure reaction times, error rates, performance in general. But we also have an EEG cap on, so we can also measure her neural activity. And this funny looking glasses, this is a mobile eye tracking system, and that allows us also to track her attentional processes as she's doing the task with the robot. So in sum, we sort of combine cognitive neuroscience measures with human-robot interaction approach, and we are very much interested in how mechanisms that have been observed in the classical lab experiments in the past, how they translate to these more ecologically valid setups. One of the key questions that we're asking is whether humans adopt intentional stance towards robots and under what conditions. So intentional stance is a philosophical concept from Daniel Dennett, and the idea is that when we interact with other humans, we predict and explain their behaviors with reference to mental states. So when I see someone reaching and grasping a bottle of water, I will explain their behavior, that they want to drink and they believe that water will ease their thirst. Believing, wanting, those are mental states. On the other hand, if a coffee machine stops pouring coffee into my cup, I'm not going to explain that behavior as the coffee machine wanted to be mean towards me and stopped pouring coffee, but rather the idea is that it was designed to behave in such a way. So intentional stance is explaining and predicting behaviors with reference to mental states, and that is in contrast to the design stance, where we explain and predict behaviors with reference to how the system was designed to behave. Now, you can already imagine that this is an interesting case for humanoid robots, because humanoid robots, they look like humans, might behave like humans. So they kind of might call for us to adopt the intentional stance. We might be tempted to do so, but we know that these are just artifacts. So do we adopt intentional or design stance? Now, before we can answer that question, what we needed to do is to actually operationalize intentional stance and the degree to which participants adopt intentional stance. That was definitely not an easy task. And that is because it's a philosophical concept. So it's very, very difficult to put numbers into something that is a very high level philosophical concept. So after about, I don't know, a year of trying out various things, we came up with this tool that you see here on the screen. So this is sort of like we call it intentional stance test. So kind of like a questionnaire type test, where participants are presented with 34 scenarios of this type. One scenario is this triplet of photographs where you see that something is happening here. There's a story going on here. So they're playing cards, and then suddenly a robot makes this kind of movement, so peeks into the cards of the opponent, and then the story goes on. And now what we ask our participants to do is to decide between two descriptions of the scenario, where one description is purely with mentalistic terms. So ICAB, our robot, was trying to cheat by looking at opponent's cards, or a mechanistic explanation. ICAP was unbalanced for a moment. And then participants take this slider and they can move it. It's an analog slider, so they can move it within that range, wherever they feel that it best corresponds to the description that best corresponds to the scenario. Now, what you can do is then you can quantify the responses, because you can recode the most mechanical description and let's say assign a 0 to this and assign 100 to the intentional description. And if you do that, on average, we get a score of between 40 and 45, meaning that participants are below 50. 50 would be exactly in the middle, right? So they are more on the mechanistic side, but not completely on the mechanistic side. And we have done this, administered this test many times across different samples, across different countries. And we usually get this, if we're talking about the general population, we get around 40. Now, what is interesting here is that what we realized is that individuals differ with respect to this number. So there will be those participants who will be more on the intentional side, and they will be more likely to score higher, and then they're pretty consistent in their scoring, and those that are on the mechanistic side. So this is something that we are trying to understand, what is actually behind those inter-individual differences. One thing that we realize that is at stake is certainly level of education. So what we see is that the more educated our respondents are, the less intentional stance they would take. And this is not surprising, because the mechanistic stance is, let's say, the vocabulary is more technical and more, let's say, less used in daily contexts. So we're not surprised by this. But we still need to understand whether it's just level of education or type of education. We also have administered this test across 2 different samples. One was roboticists, and the other one was psychotherapists. And we actually see a very large difference between those 2 samples. Roboticists, to no surprise of ours, score very low, meaning that they would almost never adopt the intentional stance towards the robots. Okay, but one thing that we were quite interested in was what happens in the brain when people are solving this task, and whether we can actually perhaps understand from brain activity what sort of stance participants would take when they will be responding in this test. So we administered this test while we measured their EEG. And we adapted the test slightly because we didn't want to have movement artifacts related to reading. So the sentences were actually delivered to participants by audio. And we looked at the epoch of EEG just before they were, so they had their hand on the space bar during the remaining time of the trial. And when they were supposed to make the response, they needed to release their hand from the spacebar. And we looked at the epoch just before their release of the spacebar. And we wanted to see whether that epoch would somehow tell us something about these 2 different groups of people. And indeed, when we looked at different frequency bands, we saw that gamma activity in this region here that you see here marked with asterisks, this is the activity where we were able to differentiate between the 2 groups of people, those that were more on the intentional side and those that were more on the design side. And that's quite interesting, because gamma activity in this region has actually previously in literature been found as correlate of mentalizing. So this is all in line with literature. Now, even more interestingly, what we looked at was resting state EEG. So this is time before participants are given the task. They just came to the lab. We prepared their head. We didn't tell them what the task is. We didn't show them the robot. And we asked them just to relax, sit still and relax and think of whatever they would like to think while we were measuring their resting state activity. And interestingly, we were able to discriminate between those 2 groups, even based on this resting state activity. Now, this time in the beta frequency band, so not in gamma, on those 2 regions here. And since we at first didn't know how to interpret this beta activity, we looked again into literature, and we found that this beta activity in the resting state is correlated with default mode network, which is a network that is related to the social brain. So again, this is in line with literature, but the most interesting part for us is that actually, even before participants do the task, you can see differences in the neural activity that then would predict what sort of stance they would take towards the robot. Now, what we cannot tell based on these data is whether this is a state or a trait. So we have not re-invited our participants again to test whether this is something that is related to a given individual. Maybe it's just that at this particular moment in time, they were in a particular state that then made them make decisions in intentional or design stance direction. So to wrap up this part of the intentional stance story, what we can say is that humans differ in their likelihood of adopting an intentional stance, and this difference can be detected already at the resting state EEG signal. Now, what I showed you so far is, let's say, baseline intentional stance activity, and this is something that we measure without giving participants the opportunity to interact with the robot and to see whether the interaction, the type of robot behavior would actually make a difference for how much the degree of intentional stance that they would adopt. So what we're interested in is whether by robot behavior, we can change that number, that magic number of 42, let's say, and modulate that number by the different types of behaviors that robot displays. So I can tell you just quickly that we have tried many experiments in which participants observed a robot with various behaviors, more or less human-like. Some of the behaviors, I mean, like, for example, eye movements of the robot that was copied from eye movements of a human. And we haven't seen much of a modulation of that baseline intentional stance score. But then we thought that maybe pure observation doesn't do the trick. So then we switched from having just observational scenarios into interactive scenarios where things actually might matter more for participants. It matters more when they're interacting with the robot, and perhaps that will modulate the intentional stance. So here, what we thought of is a task where, as I say, what we hypothesize might matter is interaction and doing things that matter also to participants. So we thought of a social activity that would be socially bonding to participants and would actually be something that they do often with maybe friends, with other humans. And we thought of an activity that would still be sort of doable for the robot. So movie watching together. So this is the task here in the middle. They would be watching a movie together. And what we do before the movie watching, we administer the half of the intentional stance test before the pre-task and half of it after. And the question is whether we will see differences between pre and post. Now, during the movie watching, in one condition, our robot behaves in a very human-like way. So first of all, it actually talks to the participant and introduces itself. And then it has reactions, emotional reactions to events happening on the screen that make sense and are actually contingent on what's happening in the video. And this is our human-like condition. And the idea here was that participants would attune to the robot while watching the movie. In the other condition, that is our mechanistic condition, the robot was completely mechanistic and had very irrelevant responses to the video. I will explain them to you in a moment. Now, I really hope that this video will work together with the sound. So what you see here is what they are watching here on the video together, on the screen together. If you can hear the sound, you hear that the robot was giggling in a very human-like way, and that indeed affected our participants because they started laughing together with the robot. So there were different behaviors of the robot. Some of them were responding in this kind of giggling way. Sometimes the robot would be very, very sad because there would be a tiger attacking another animal and would be terrified by the situation, then sad. Sometimes the robot would be in awe with a beautiful view and it would express with its entire body its reactions. Now, in the mechanical condition, so our control condition, the robot we still wanted to have the same amount of events happening in this test. So our robot would still produce sounds and produce movements, but it would just be like an artifact, like a car, for example, that is signaling to you with beepers that you're approaching an obstacle. So it would, when there would be an event on the screen, the robot would go like beep, 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 beep. And so it was a very, very mechanical behavior. And these are the results. So what you can see here is our intentional stance score before, and it's around our magic number 40. And it increases quite substantially after having the interaction with a human-like robot. Now, since we have had several failures of actually not seeing any modulation of the intentional stance score before in these observational studies that I mentioned to you, I didn't want to believe that this actually is a true effect. So I asked my students to replicate this effect. So this is what you see here is an identical experiment than this one. The only difference between those two experiments is the way we split our intentional stance test into those two halves, because as I said, we have to have half of the items before and half of the items after. So we just basically reshuffled those items in a different split. And otherwise we did exactly the same experiment. And you see that we replicated the effect. And what I can also tell you, I don't have the data here, is that we replicated it again in Singapore. So with a completely different sample also with different cultural backgrounds. So this shows you that the effect is very robust. And I think it's also like, if you participate in this experiment, it's quite an evocative experiment. Now, what you see here in the rightmost panel is the control conditions. So where the robot is behaving completely mechanistically, and there was no difference between pre and post intentional stance score. And that really tells us that actually it's not just the mere exposure to the robot. What mattered is this human-like behavior indeed, as we hypothesized. So, okay, based on this, we thought indeed what matters is to interact with the robot, to do something together. So here's another experiment where participants are involved in a joint task with the robot, and it is joint in the sense that they can achieve this goal only together. And the goal is to move. This is actually a task that I will later talk about in the context of sense of agency, because this is a task designed to measure also a sense of agency. But here I just wanted to tell you very quickly about the intentional stance test. So what participants need to do is they need to move the white cursor, you'll see in a moment in the video. They need to move the white cursor to their target location, this black rectangle here. And one of the actors is the so-called mover. So they're responsible for moving this cursor. And the other one is supposed to just detect when the cursor is already there on the target. So kind of confirm that the cursor is on the target. And after that, they will hear a sound, and that was made for the sense of agency that I'll talk about later. Now, the important part here is that they are doing complementary actions and they need to achieve that goal together. And again, we administer intentional stance test pre and post. And this is how it looks. So now the robot was the mover and the human was the detector. This is roughly how it looks. And also with this task, we see that our average intentional stance score increases after the interaction when they're doing this task together. So all in all, we showed that we can modulate the baseline intentional stance score by an interaction with a robot that either does something with you or behaves in a very human-like way, but also in an interaction. Now, the question is, can we also down modulate the score? So can we destroy the intentional stance? And this is actually an experiment we run even before those that I was telling you about just a moment ago. This is an experiment where we were interested in joint music playing, so joint action. Well, it's a little bit of a complicated design, but I'll guide you through this very quickly. Don't worry about the amount of text. So basically what participants are doing, they're asked to generate a sequence of taps on a tap screen that is vertical, you'll see in a moment. And each tap is a sound. So in the end, they're creating a melody at their own will, whatever type of melody they would like to do. And once they have themselves memorized the melody that they created, they then teach it to ICAP. ICAP at first is quite delayed with sort of following the taps, but then it's faster and faster. So it eventually learns, it shows as if it learned the melody quite well. And then they're playing in a duet. In a duet, ICAP is supposed to start and the human is following, but the task of the human is to get as synchronized as possible with ICAP. And so the important manipulation here that we do is that ICAP will make some errors every now and then. And that's why we had this teaching phase where we wanted participants to make sure that participants understood that the robot knows how to do the task. And it would do the task properly, but then sometimes it would make errors. And those errors would be either human-like or very mechanical. And you will see in a moment in the video. So this is, please just signal to me that you can hear the sound. Great. So this is a simple melody, of course. And you see that the robot swapped the two taps. So it could happen to a human if you just make a mistake by tapping the wrong button. Now this is the machine-like error. The robot gets into a loop and it doesn't recover. So when you see the machine-like error, you see that the difference between human-like and machine-like is quite striking. And indeed, the machine-like error is not an error a human would do, at least not a healthy human. And so with this, we actually managed to down-modulate, or managed. We didn't want to down-modulate, but we see an effect of down-modulation of the intentional stance score. So in the mechanical condition, there's a reduction of the score. In the human-like condition, there is no difference between pre and post. And now maybe something like just a digression, a little bit of a digression here, because I think it's quite interesting. It's not about intentional stance, but I just wanted to mention to you here that we looked also at the variability and asynchrony between those two conditions. So how actually participants, how variable their taps are with respect to this, the duet playing together. And what we observed is that the variability in human taps decreases in the human-like condition. And that's quite interesting because a decrease of variability is a signaling behavior that we use and also other animals use to signal the willingness to cooperate. So if you want to compete with, if an animal or a human competes, then you increase variability because you want to be more unpredictable, while decreasing variability signals cooperation. That's quite interesting because we observe this effect here as a function of the two conditions. Okay, but this was just a digression. So the intentional stance, to conclude, interaction with the robot might modulate the degree of adoption of intentional stance, and this kind of liking and social bonding increases while mechanical behavior decreases the degree of adoption of intentional stance. The second part of my talk is about the sense of agency that I think is a related topic to intentional stance. And I wanted to tell you about the line of research we're doing also in my lab on the sense of agency. So I'll start with the vicarious sense of agency here. And so the idea that you experience sense of agency over someone else's actions. So sense of agency defined as feeling of being in control of actions generated, of their generated actions and their outcomes. And interestingly, people can experience this kind of sense of agency over another person's actions and outcomes. And this is what we call vicarious sense of agency. Now, the interesting part is that we saw in literature that vicarious sense of agency occurs only when the other agent is another human, not when it is a computer. So we asked again the question, what happens with robots, embodied robots? For that question, we use the intentional binding paradigm. So this paradigm developed by Patrick Haggard and colleagues quite a while ago. And I'll guide you through the paradigm because it's a little bit complicated, but then once we are all on the same page, it will be easier to tell you about the results. So the intentional binding is a phenomenon that when you produce yourself voluntarily a certain sensory consequence of an action, the temporal interval between the action and the sensory consequence shrinks. So the perceived interval between those two events seems to be shorter than it actually is. This is related to the forward model and your ability to predict the sensory outcomes of your own actions. Now, this is how a typical intentional binding paradigm looks. Our participants are observing a Libet clock running continuously on the screen. And there are four conditions typically in a paradigm like this. So one condition is, there are two baseline conditions. One is the baseline action and baseline tone, meaning that you only press a key and you're asked to judge later on at which point in time did you press the key. The other one, you just hear a tone, okay? And then again, on the clock, you have to estimate when you heard the tone. Or there are the two operant conditions where you do both. So you press a key and you hear a tone. In one condition, you are asked to evaluate when you press the key, but you also hear the tone later. And the other one, you're asked to evaluate when you heard the tone, even though you did both things, so press the key and hear the tone. Now, then you have to give a response later based on the clock. Where was the clock hand as the critical event occurred? Now, this is how the situation, our dependent variable that we'll be looking at judgment errors. So if you think about the starting position of the clock, the actual occurrence of the critical event, then there's the perceived occurrence of the critical event. So there's an error, and typically we make errors even in the baseline conditions. I'll just explain that in a moment. So this difference between the actual and the perceived occurrence of the event is our judgment error, and this will be our dependent variable from now on. Now, if you think about the action event, what happens here is that we have our reality, so when the event actually occurred. In the baseline, we typically underestimate our action. So even if there's no event later, no tone, I just press a button press, I will typically underestimate the button press because I'm the one who's producing this event. Now, in the operant condition, this underestimation will actually be less because as you remember, the time shrinks between the action and what will happen later, the tone. So the perceived action is moved towards the tone. I hope this is clear for everyone. So actually the judgment error is, let's say, less of an error in the operant condition because it's closer to the tone. This is when we ask about the action event. In the tone event, we have an opposite situation. So this is our reality, 0. Then what we have is an overestimation of the tone event. And in the baseline, and in the operand, again, because they are being brought together, the action and the tone event, what you see here is less of an overestimate. So typical, but not always, typical result is that in when we ask about tone events, we get values in the positive range, when action events in the negative range. So one of the questions we were interested in is how much sensory motor action representation of another agent plays a role in this kind of vicarious sense of agency, because we knew from literature that vicarious sense of agency occurs with humans, but not with computers. And the other question was attribution of intentionality, whether there is a relationship between those two. So in our two experiments, this time not with the ICUB robot, with just a toy commercial Cosmo robot, we were asking those questions. And what we did is we had these conditions. In one condition, we always have an individual context just to compare to the kind of baseline effect that should be there, and the social context with physical action, where our robot is making the button press actually physically pressing on the key. And then we have a second experiment with the digital action, where the robot is not pressing. So this is about the sensory motor representation of an action of someone else. We're interested in whether the embodiment and sensory motor representation play a role in this vicarious sense of agency. So in this is our little Cosmo robot, and what you'll see here, it presses on this cube. That's when the action happens. This is our Libet clock, and this is our physical action. I'll just show it to you. That was just pressed with this lever on the cube. I will not go into the digital action video, but basically what we told our participants is that the robot sends via a Bluetooth, sends a command for the tone to happen, for the computer to play the tone. So there's no physical action involved there. These are our results. When you look at the physical action, and we are now talking about evaluating the tone event. So we're asking participants when tone occurred. When we have the physical action on the Cosmos side, we see vicarious intentional binding effect. It's comparable to the individual condition. So basically, participants adopted this kind of vicarious sense of agency towards the robot. When there's the digital action, the effect is not there in the social context. This is what exactly what we expected if sensory motor representation matters for these effects. Now, this is tone event. Now, if we talk about the action event, when we ask participants to evaluate the action, the situation is a little bit more complicated, because things are usually complicated in empirical work. And also in the physical action, we do not see vicarious intentional binding effect in the case of this little robot that is not a humanoid. For the digital action, we see a reverse pattern. And this is something I will not go into details because this gets a little bit complicated, but this has been observed previously in literature in involuntary action. So this is quite interesting as well. When you have a situation where an action is produced, but it's involuntarily produced, sometimes the effect reverses. But let's focus on this one, on the physical action, because that's where we expected actually the effect to be there, and we don't see it. So we looked into intentionality attribution and wanted to see if that is somehow related. We administered before the experiment a scale for intentionality, the White scale. And what we see here is that on the score of the White scale, there is a correlation in our first experiment, so the physical action experiment, between the degree of intentionality attribution to robots in general and the effect. So what we think is that there is probably also intentionality, attribution of intentionality plays a role to some degree in this vicarious sense of agency. But this is with a non-anthropomorphic robot. Now, what happens with the ICUB, where we expect that the sensory motor representation of the action of the ICUB is even stronger, because it's exactly like it's very, very similar to another human embodiment. And we asked the question about the action event, so the one that was a little bit not clear in the Cosmo condition with the robot. And what we see here, it's maybe not very clear with the graph here, but we see the main effect of intentional binding, both for the solo and the social context, meaning that the effect is there with the ICAP robot. It's not like it was in the case of Cosmo, where that was not so clear. So we see the effect here. And in addition, we also see a very strong correlation between the right score and the intentional binding effect. So it kind of boosts the effect even further also in the humanoid condition. All right. So based on this set of studies, what we can conclude is that when we have a digital action, we sort of don't really represent how this action happens at the sensorimotor level. We don't activate that mechanism, and therefore vicarious sense of agency never occurs. And this is the same case as with computers, disembodied computers. Now, physical action performed by a non-anthropomorphic robot like the Cosmo, we have some sort of a representation because it's physical enough, but it's still different. The motor repertoire is different than our motor repertoire. Therefore, this sort of needs a boost perhaps from the intentional stance. And then finally, a physical action that is performed by a humanoid robot, we have quite a good accurate representation of the actions, and we see vicarious sense of agency emerging. That is the relationship between sense of agency and sensorimotor representation. Now, the relationship between the sense of agency and intentional stance is that with the digital action, there's no relationship whatsoever. With physical action, the vicarious sense of agency emerges as a function of intentional stance, and with the physical action performed by a humanoid robot, there's even an additional boost by, let's say, intentional stance. Okay, so to conclude this part, both action representation and intentionality play a role in the emergence of vicarious sense of agency. Now, this is the experiment that I mentioned to you earlier, that when I was talking about the intentional stance. Here, what we ask participants is, or what we asked through this experiment was joint sense of agency. It's slightly a different concept than vicarious sense of agency. Here, the idea is that you co-represent yourself and the other agent as one team, and you generate a joint sense of agency. In this complementary, you might remember that participants in the robot are doing a complementary action. So one of them is moving the cursor, and the other one will be detecting the cursor on the target location. And then after the detection of the target, a tone occurs. And again, we're looking at the temporal estimate between the final press and the tone that occurs later. Now, there's an interesting question here. What happens when you have those two different roles? Because when you're the mover, you're not actually the one who produces the final action that produces the sensory effect. So only if you are forming this kind of joint sense of agency, you would see the effect independent of the role that you're playing in this experiment. This is inspired by a paradigm that has been introduced by other researchers. This is the reference here. It has been done by them with 2 humans. And basically what they found is, please forget about these 2 bars here about near and far from fixation, because they manipulated also the distance. But what matters is that there was the same kind of level of temporal estimate. This time we're talking about temporal estimates, not judgment errors. So you basically ask participants to estimate how much time has passed between one and the other event. Those temporal estimates did not differ as a function of the role that participants played, whether they were the mover or the detector. And that shows that they formed a joint sense of agency. So we did the same with 2 humans and also with the robot. And these are our results. So when we look at this with having a human confederate as a partner, we replicate the results of the other paper. So independent of what role you play, you see the same level of the delay rating, meaning that you adopt this kind of joint sense of agency in this context. Now, interestingly, when we have ICAP as a partner, there is a difference here in this one condition where the human is just the mover. So that means that human is actually not producing the final click and the very final outcome. What happens here is that it's the robot producing this final move. And the larger the temporal interval, the less sense of agency there is. Because remember about the shrinking aspect, so the more the shrinking happens, the shorter the interval. So that means that with our robot here, they haven't formed really a joint sense of agency, because when the robot was the one who was producing the tone and they were just the mover, they had less sense of agency as compared to these other two conditions. But now, interestingly, what we did is we run a third experiment in which we boosted the intentional stance through the manipulation with the movie watching, that you remember that the robot was giggling, and we know that this manipulation boosts their intentional stance. And we wanted to see if we boost the intentional stance before the experiment, before this task, whether we would get to the human level. And in fact, this is what happens. So when we ask our participants to first watch the movie with the robot, we measured their intentional stance with our test because we wanted to make sure that actually the manipulation worked, and it did. And what we observe is that the bars are statistically at the same level, and they're comparable to the human condition. So once we boost the intentionality, again, we can see this joint sense of agency occurring. So attribution of intentionality seems to play a crucial role in establishing joint sense of agency. And the very final experiment that I wanted to show to you and talk to you about, it's going to be probably 3 minutes. Can I still have those 3 minutes time? Okay, great, thank you. It's a nonverbal Turing test that we have done quite recently in our lab. This is a test in which we thought, okay, we are not happy with having just one robot. Now we want to have 2 robots in our experiments. So what we did here is we asked our participants to come to the lab in dyads, and each member of the dyad was placed in a separate room with one ICAP. So you see our participant 1 and ICAP 1, participant 2 and ICAP 2. And they are performing a very simple task. It's a joint Simon task. So basically, all they need to do is respond to a colored square presented on the screen. So for example, in this case, ICAP's task would be to just respond to a green square as fast as possible, and her task would be to respond to a red square. So they have just 2 different roles. And now the manipulation, that the most important manipulation for us that we did was that in one condition, ICAP was pre-programmed, and in the other condition, ICAP was this ICAP was controlled by the other member of the dyad. So it was kind of teleoperated by the other member of the dyad, and vice versa. This ICAP was either pre-programmed or controlled by this person here. And now our question of interest was whether people would be able to distinguish those 2 conditions, the human operated or the pre-programmed condition. And they had very little hints because they didn't talk, they didn't have any other information, just the distribution of the reaction times of their partner. So they could just look at how the partner responds. Now in the pre-programmed condition, what we did was we actually took data from another experiment where this experiment was done with 2 humans, and we made it in such a way that it was less variable than in the human condition. So this is our computer pre-programmed condition. You see here the distribution of reaction times in this computer condition, how we pre-programmed ICAP to be. It's much narrower. The question here is whether, based on such a subtle hint in behavior, people would be able to distinguish these 2 conditions. So this is the human controlled. So this is actually our participants distribution. And this is our modified distribution that we pre-programmed the robot with. And is that an enough hint to be in the, let's say, human range reaction times, but with a different shape of the distribution. These are the data. So this is our Turing accuracy rate. And what you see here is that in the human condition, they were actually above chance in distinguishing the humans. So they had enough sensitivity to capture this distribution of human responses. And that's our human condition. Now, in the computer condition, they were in chance. They did not differ from chance. And that sort of tells us that it's sufficient to have this human-like range of reaction times for the program not to be really distinguishable. I mean, it's to blur the distinction between whether it's human-controlled or pre-programmed. So humans do have sensitivity to human-like behavior, variability, even with very, very subtle hints. Variability is a very important factor in behavior. That's something we're beginning to properly understand only now. But behavioral variability within the human-like range, even though it has a different shape, blurs the distinction between human and machine. Okay, so I would just like to come to the conclusions that to tell you that robots might actually evoke adoption of intentional stance, especially if they are engaged in a social interaction with humans. Vicarious sense of agency towards robots depends both on sensorimotor representation of an action and on intentional stance. And joint sense of agency with robots emerges as a function of intentional stance. Now, these are a few questions that I thought I would put up here for discussion, because I think the idea is also to discuss. I hope it's going to work somehow. But one of the key questions that we're still trying to understand is what is the relationship between intentional stance and social attunement. What I started this whole research program with was the idea that maybe intentional stance is needed to attune with others. Now I'm beginning to think is that actually it's social attunement first. If you attune with a robot, and this is something we saw with those experiments with movie watching, for example, together. If you attune with a robot, then you might adopt intentional stance more likely. And that's because the robot becomes more like me. The second question is more like, let's say, philosophical and ethical. Is it actually correct to induce intentional stance in people, whether we should do this? I mean, machines should probably just stay perceived as machines, and maybe it's not completely ethically correct to do this. But I think what we're doing in our research program is just to understand at first what are the conditions in inducing the intentional stance, and then one can make informed decisions. And then finally, what are the application contexts where this actually might matter? And here what you see is a picture of another research line in my team, where we are bringing robots to assist therapists in training for individuals with autism, and they train social skills, and we have very, very interesting and promising results in that. So that also kind of calls for a question: what sort of application contexts we want to have intentional agency. And with this, I would like to thank my team and the funding agency, the European Research Council, and thank you very much for your attention.
Thank you.